Hello dear students, welcome to Nuclear Physics 1 lecture number 5. I'm Dr. Pervez Ahmed. In this lectures we will continue our discussions on basic concept and nuclear physics. In today's basic concept we will deal with the nuclear stability. We will discuss that what is mean by nuclear stability, and and we will also have a discussion on what is mean by a stable nucleus and unstable nucleus. So let's proceed towards today's lecture. First we should have some formal definitions of nuclear stability. You should know that what is mean by a stables or non-radioactive nucleus or nuclei. What is mean by a stable or non-radioactive nucleus? So, a stable or non-radioactive nuclide is one whose atoms do not decay. We have already discussions on what is actually mean by decay. Decay means it's a process in which an element undergoes disintegrations. It is divided into parts, into subparts. So that process is called decay. This is somehow a formal definition for a stable and a stable nucleus, or the stable nucleus we also call non-radioactive. It's a sort of the nucleus that do not decay to other elements, or it do not disintegrate. It's a definition for a stable nucleus, or the stable nucleus we also call non-radioactive nuclei. If you plot the stable nuclei, so we will get an interesting patterns emerges, and that is being shown on the next slide. So you will observe that. So in that particular graph that we will show you on the next slide, it's basically a plot of neutron number that we represent by n versus the atomic numbers that we denote by z for the stable nuclei. So here is that it's the line of stability. It's the most popular line that is known as the line of stability. Here you can see that we have plotted the number of proton versus the number of neutrons, and this line is basically known as the line of stability. So here you can see that this linear line. Here you can see, these dotted lines. These are basically, it's the line that show that the number of neutrons is equal to the number of protons. And here, these dotted, it shows the nuclei as the number of nuclei which contain more neutron than the protons. So this basically represents those nuclei. Here we have more number of neutron in comparison to the proton. So we have these two lines. So this line in which the number of neutron is equal to number of proton is basically known as line of stability, and this is the line where the number of neutron is greater than the number of the protons. So let's have further discussion on this line of stability and what it has to do with the nuclear stability. So you should remember that for the heaviest stable nuclei, neutron is about 1.5 times the number of protons. This is the possibility for the heaviest nucleus. Some sort of condition for the heaviest nucleus. If we have a heaviest nucleus and we want that heaviest nucleus to be stable, so here is the conditions. It should have the neutron. It doesn't matter whether the number of neutron is greater from the number of proton, but here is the conditions that the heaviest nucleus will remain stable if the number of neutron it contains is about 1.5 times the number of proton. So this is the condition for the heaviest stable nucleus. That is, we can have a heaviest stable nucleus with these particular conditions. So the presence of the extra neutron, here's one can have the questions that what should be the role of the extra neutrons in the heaviest nucleus. If you have a heaviest stable nucleus, so what will be the role of the extra neutrons? So the presence of the extra neutrons basically overcomes the positively charged protons' tendency to repel each other and disrupt the nucleus. I mean, uh, somebody may have a question in mind that neutrons do not have the charge. So how can it disrupt the positively charged proton? Let me tell you that protons and neutrons among the protons basically separate it's further separate protons from the proton. So this statement actually create that particular sense, that is, the more you separate the protons, so the more weaker the Coulomb repulsions will become. So I mean, it's this actually mean that particular sense according to Coulomb law. So but along with that, you should remember, I mean, here one have the question that in nucleus we have only positively charged protons, and positive they repel each other. So how the nucleus is remain stable? So I mean, the answer is lying here, that is, the nucleus is held together by a poorly understood force that is called the nuclear force. And this nuclear force is much greater in magnitude in comparison to the Coulomb repulsive force between the protons. But this force it has some restrictions that we have to discuss further. So the nuclear force is extremely short range force. What it means? It means that what is mean by the short range force? So it means that it acts over a very it acts over a maximum distance of about 2 protons diameters. I mean, from short range, when we say that the nuclear force is extremely short range, so from short range, we specify the distance over which the nuclear force is operational. And how much this distance should be, so it is clarified here that it should be equal to about the distance of 2 protons diameter. I mean, the nuclear force will be operational between the 2 protons, or between the proton and neutron, or between the neutron and neutrons, if the distance between them is equal to about this particular estimate, that is about 2 protons diameter. So if they have this much of the distance, so only then the nuclear force will be operational among them. Otherwise the nuclear force will be weaker in comparison to the Coulomb repulsive force. So what it means? So it means that for the nuclear stability, the force that is responsible is called the nuclear force, and this force is somehow playing the force of like binding energy force. I mean, we can call the nuclear force somehow as the binding energy that hold the nucleus together. I mean, the strong nuclear force is somehow a binding force that bind the nucleus together inside the nucleus, in spite of the repulsive force between the neutron. But since we mentioned it's a short range, it's act between the two nearest neighbor nuclei, so that's why it's unable to operate for a large distance. So in order for this to be for the nucleus to be stable, so the nuclei should have the distance in this particular range. Only then it will be acted upon by the strong nuclear force. So now you are familiar with the stable nuclei. Now you should also know a bit about the unstable nuclei. So what is mean by the unstable nuclei? So it is basically the nuclei which do not fall on the line of the stability tend to be unstable or radioactive. Let me clarify it again. What is means unstable nuclei? So we have nuclei which do not fall on the line of stability and tend to become unstable or radioactive. I mean, from unstable nuclei, we mean those nuclei which do not fall on the stability line, and these nuclei, they are unstable or radioactive. So what is mean by that? It means that they have a certain period of time that is called half-life, after which that nuclei, that particular nuclei, we have a natural decay process or disintegration process. The division start in that particular nuclei. So that's why we call that unstable nuclei or radioactive nuclei, and they are also called radionuclide. So a few radionuclides do not fall on the line of stability, but their rate of decay is so slow that for all the practical purposes they are stable. We have some radionuclei that do not fall in the line of stability that I have already shown on the previous slide. But we remember, and the reason for that is that their rate of decay is so slow that for all the practical purposes they are stable. Just because of their decay rate, their decay rate is very slow. So just because of that, these radionuclei, they are being used for all practical purposes, and those particular purposes they are being treated as like stable nuclei. So radionuclides undergoes a process called reactive transformations or disintegrations. So what actually happened in the disintegration process? So in this process, the nucleus emit particles to adjust its neutron numbers to proton numbers ratios. And disintegration process are and radioactive process are, we can say that, and radioactivity, basically the nucleus, a particular radioactive nucleus, it emit particles, and the reason for the emission of this particle is to adjust its neutron to proton ratios. Radionuclide continuously they are emitting the particles, and during these emissions they're trying to maintain their neutron to protons ratio. So this change in the neutron to proton ratio tend to move the radionuclide towards the lines of stability. The process of the ratios is continue. Sometimes the number of neutrons increases, then the number of protons, and sometimes the number of protons it decreases, then the number of the neutrons. But this change, this change in the number of neutron to protons basically tend to move the radionuclides towards the line of stability. So some common radionuclide include naturally occurring uranium-235 and uranium-238, cobalt-60, cesium-137, strontium found in nuclear power plants, iridium used in radiography, technetium used in nuclear medicines, iodine used in treatment of thyroid conditions. These are some of some commonly used radionuclide. So that's all we have for this lecture. Hope you enjoyed and learned a lot. Thanks for watching. See you in next lecture on Nuclear Physics 1. That will be lecture number 6. And that particular lecture again, we will proceed with the basic concept in nuclear physics. And you already seen, you already can see those, concept. So stay tuned for the next lectures. See you very soon. Till then, bye-bye.